So we're going to start the next session. I've learned the microphone is not for my voice amplification, it's for the people online, so that's reassuring. The next speaker we have is Vadim Shcherbakov from Royal Holloway, University of London, so a neighbor. And he'll be speaking about diffusion limit for a model of interacting spins, Qs with a log linear interaction. Thank you.
Thank you very much for the organizers for the opportunity to give this talk, title of which you can see on the screen. This is joint work with Anatolii Puhal'skii, my collaborator from IITP Institute, Dobrushin's laboratory. He's working now. Let me start with the model. So it's a simple discrete model. It's continuous time finite Markov chain, components of which are labeled by vertices of a graph, finite connected graph. And there are two parameters of this model, n capital, which is integer, and the real numbers alpha, beta. And the components of the Markov chain take values in the set of this set, first n+1 non-negative integers. And the dynamic of the model is as follows. So it's it's continuous time. So a component which is less than n capital can increase by 1 at this rate, which is the birth rate. And any non-zero component can decrease by 1. So this is birth and death dynamic. And this is, you can see, let me, sorry. Right. So how this model is, motivation for this model. Original motivation that my motivation for studying this model, some time ago I came across cooperative sequential model, the model which is widely used in physics for modeling various adsorption processes. So you can imagine surface of a material, particles diffusion around. When they hit the surface, they might get adsorbed, and the adsorbed particles change properties of the material. And so next particles might be more attracted or repelled by already existing particles on the surface. So how this can be, dependence can be modeled. So this is one of the, this is, sorry. Is it first? Sorry. Right. So birth rate here. So here you see that birth rate depends on the value xv, number of particles at vertex v, and then also on the number of particles in the neighborhood. And they affect differently the birth rate. It's alpha, beta, so they're separate. So interaction here is embedded into birth rates. Constant rate is just for. Sometimes the adsorbed particle can depart. It's called desorption. So that's death rate. Another interpretation. Sorry, another interpretation. The model is actually in the spirit of models of statistical physics, interacting spin system. But it can be also interpreted as a queuing model because the components are non-negative. So it's exponential service times, if you prefer to look at this from the point of view of queuing model, queuing theory. And here, like I already said, the interaction is you can rewrite birth rate like this. So this is this factor interaction in the model, and this is a shorthand notation for the interaction term in terms of the adjacency matrix of the graph, So this is definition of the adjacency matrix. And if you don't want to have interaction at the birth rate, you can move it into the death rate, just simply moving this term with the minus here to death rate. This is a related model. So where interaction built into the death rates. Any questions? Is the model clear? Graph is finite. It's finite Markov chain. It's very simple model, continuous time, finite Markov chain. Yeah. So bounded. At the moment, bounded. N is this n. It's fixed capacity. So there's maximal capacity. So if there is no space left, then no particle can be. They can only decrease, right? So sorry. And what can you say about this model? It's a reversible model, easy to check, and the stationary distribution can be easily computed. And this is how this stationary distribution looks like. And the related model with tilde I mentioned also, it's also reversible with the same stationary distribution. You just write the detailed balance equation. You can move this interaction from one side to another. You see that works for both of these models, right? So and when n is n capital is finite, so that's not much you can say about this model in addition to what already said, right? It's let's examples. So if just a single vertex, then we have birth death process with reflection at the origin and the right point n capital, and this is how the station distribution looks like. If we have two neighboring vertices, then this is how the station distribution looks like. Two interacting components. N equals to 1. It's a special case. In this case, we get special case of Ising model, the famous model in statistical physics. Only this model is usually components -1 + 1, which can be easily obtained by just linear transformation this spins from 0, 1 to -1, 1. And you see it's just special case of Ising model, right? Okay. Right. So keep pressing the wrong direction. So what you asked about n, if n, we just set up n to be infinite, just formally, and consider the same dynamic, the Markov chain becomes countable, and dynamics already not so trivial as in finite case. It can be in continuous time, it can be explosive transient, non-explosive, null recurrent, positive recurrent, null recurrent. And depending on the parameters of the model and structure of the graph, all these possibilities realized in this model. I'm not going to provide complete classification for different parameters, but this is just some examples here. So for example, this Markov chain is positive recurrent if and only if this condition satisfied. Well, lambda 1 is the largest eigenvalue of the adjacency matrix, which is also known as the principal eigenvalue of the graph. Right? So this, only in this case, the function I showed you before is a summable function if we consider states from this non-negative set of non-negative octant or octant. No, you see what I mean. And then stationary distribution is given by the same formula as before, but only, like I said, the states are from this set, but the same equation. And if alpha negative beta is equal to this one, this minus alpha over lambda 1, then it's non-explosive transient. And if, say, alpha positive, then regardless of beta, it will be always explosive transient. And sorry, again, wrong direction. Just another example. If this is constant degree graph, no, for example, just two vertices connected, the simplest one, then we cannot use this case to illustrate phase transition in the long-term behavior of the model. So if we fix alpha, parameter alpha negative, and then Markov chain is positive recurrent if beta is less than this quantity. We start increasing beta. If beta is equal to this, exactly equal to this quantity, then it will be non-explosive transient. And right after that, it becomes explosive transient. This is in physics what they call phase transition, some sharp, drastic change in the behavior of something, of some quantity. In this case, this the quantity, but long-term behavior, right? So and it's not a new model studied in various directions. It also can be considered when you set up depth rate to 0, then it will be just a growth process with log linear interaction. And with several people, we studied this model in various variants. And if you're interested, you can find all the references in my recent review, which is also available on arXiv. But what I'm going to talk about now, today, so recently we found that there is one more point of view on this model. So suppose we can see the model in the this regime. When n goes to infinity, we start stretching the set of possible values, and at the same time, interaction weakens. In particular, this parameter beta, no alpha as well. So precisely, so we can see the sequence of models with the parameters n capital, which is depends on this index n small, and the parameters alpha beta scaled like this, right? And consider the rescaled process with renormalized time, which is diffusion, called diffusion scaling, right? So it turns out that if we say a little bit more about this regime, then something something non-trivial appears in the limit as n small goes to infinity. So first, results. Suppose that this n capital goes to infinity, divided by n small, it goes to 0. But if you divide it by square root of n, that it goes to infinity, right? So, and this is a set of initial states of the rescaled process. Suppose it converges in probability, or it can be just non-random deterministic sequence converging to certain limit point in this set. Then this rescaled process with renormalized time converges in the Skorokhod space in the usual Skorokhod convergence in Wick sense to continuous path process. It's multivariate process, components of which are labeled by the vertices of the same graph. And this is the components of components of the limit process satisfy this system of stochastic differential equations. So here, A is the adjacency matrix of the graph. B capital is this sequence of set of IID standard Brownian motions, labeled again by the vertices of the graph. And this is the term here, which is reflection at the origin, responsible for the reflection of, at the origin of component xv. So this is how it's usually explained, right? Beta, that's a parameter of the model, alpha, beta. So alpha is pre-dynamic, and beta is interaction, responsible for interaction. So if beta is 0, then we have set of independent Ornstein-Uhlenbeck processes. That's what they call it, with the reflection at the origin, right? But if beta non-zero, then we have interaction. It is linear drift. So it's I do not provide any reference, but the paper by GP and Ishii. It's several papers. So at least one of them is this one. There is a unique strong solution for this system of equation, because it's Lipschitz linear drift, so constant diffusion, and that's normal reflection. Right? It's normal reflection, which is there is no, because these are independent. It's no problem with these covariances, these directions of reflection at the boundary. Right, and another situation, suppose that this is the same, n capital goes to infinity, n capital divided by n goes to 0, but this one, if you divide by square root of n, it tends to b, where for some finite b, finite limit. So it's I call it finite reflection barrier on the right. So in this case, the same statement, but basically the same equation, but additional term here, which is reflection process at the right endpoint. The barrier on the right is finite, so there is reflection there, right? So is the process all right? Clear? I mean, double reflected, yes, double. For each component, double reflected, yes. So this is what we need to say about these processes. As usual, reflection at the origin, reflection at the right barrier, right? And so the model actually can be regarded as a queuing system in heavy traffic limit regime or critical load condition. So why is this? So if we consider birth rate for the this process with the parameters alpha over n, beta over n, and this is how the birth rate looks like. And then if we consider sequence of states from here, such that if you multiply divide by square root of n, they converge to some finite limits, then this equation holds. And this is reminiscent to a heavy traffic limit in queuing. Basically, that's how it is written in terms of service rates and scaling parameters. Right. So this is what this is actually the drift in the limit equation on the previous slides. So so the method of the proof. The method of the proof, we apply the technique which is developed for the Markovian queuing systems. It's martingale technique, well-known technique. I think for many people in this room, at least, this is not not a novelty, and which is used for proving fluid limits, diffusion limits in heavy traffic, in the heavy traffic limit, which is combined here with Skorokhod reflection, because we have got reflection here. And the first step to rewrite by using Markovianity of the model, rewrite it in terms of the dynamic of the queue in terms of Poisson processes. This is arrival, input to the system. This is output, service, process responsible for this, for the departure of particles from the system. These are independent Poisson process with the unit rate. And this is from Markov, because it's Markov model. We can write it always like this. And then the usual trick is to, control. Usual trick is to rewrite it like this. So just to have this term here, a couple of martingales. These are martingales, MV1, MV2. These are martingales. These are reflection processes. And that's what we can say from general theory about these martingale processes. They are orthogonal system of orthogonal martingales, and these are the predictable angle bracket processes corresponding to them. That's very basic stuff actually. And so what we have here is the drift term, diffusion, which is this martingale path, which converge, which will give in the limit after rescaling gives square root of 2 times b, because we have convergence to two independent Brownian motions. And the key words for the rest of the proof is we show tightness, CLT for martingales used for getting Brownian motions, continuous mapping theorem, and the Lipschitz continuity of the Skorokhod reflection map. All this combined gives us the result. And of course, when the finite barrier on the right is the reflection barrier on the right is finite, proof is simplified because the process bounded by nature. You don't need to show boundedness of the process. And we don't claim any novelty to the proof, but due to the presence of interaction in the drift term, at certain point, you need to take this into account. At the point, if it tells you something, you apply Gronoval and Bellman inequality to show boundedness of the process, then you usually have process on the left side and function of the process on the right side. Now in the right side, the function of the also on the neighbors, and then you have to deal with this somehow. But turns out not difficult. Well, we dealt with this at least, so it's a problem removed. This problem removed. Otherwise, it's more or less the standard technique. And that's it. And the final word about the limit process. The limit process is non-explosive Markov process. If B defined the barrier on the right is finite, then it's on a compact state space. This is the distribution, stationary density of the process, which is basically obtained from this discrete, from the stationary distribution of the discrete model. Here you see the discrete case, there is this linear term here, which in this scaling just disappears. What is left is just the quadratic one. It's basically this, if you look at this, it's a Gaussian density conditioned on to be in this set. Where is it? This one. And the same, similar in the case of the infinite limit barrier, right? But now, of course, it's the state space is not compact. You need to take care about integrability of the invariant density, and that's exactly the condition that we had in the discrete case. It's basically the same. And for the process here, it's full classification is also available, but I'm not going to. Oh, this is one more example. It's one-dimensional example for undergraduate courses in advanced probability can be used. Actually, the model can be used for teaching Markov process. It's fresh example of Markov process, very mathematically tractable model. I advertise it actually as whenever I can. And I think it's Thank you for your attention. This one. Okay. Okay.
Okay, thank you. We have a few minutes for questions. Yes.
Will it be possible to consider infinite graph, say lattice in R2, but it's locally connected and it might be to pass to a limit?
Oh, well, when graph is finite, you don't need to take care about existence of the process. When it is infinite graph, you need to take care about,
Yeah, sure. So
and this is additional problem. Additional problem you need to first to ensure existence of the dynamic. It doesn't it exist for any finite time and well defined. I haven't thought about this.
thanks.
Any other questions?
Is there a paper?
Soon.
Sure. Yeah,
Soon.
I'd like to have it.
So let's thank our speaker again.